can be a list of numbers that has some sort of a pattern. Here are three specific sequences. The power in modern day mathematics is to find a pattern in something and predict what's going to happen. That's the power of mathematics. This is why statistics has exploded as a field. The better your statistics are, the better your statistical models are, the better chance you're going to have of predicting in the future what's going to happen. Okay? A business model is exactly that. As we all know, around December, sales tend to explode, right? And then after that, not as much. You know, no one has any money left in January because they ran out. So there's patterns all over the place, and the better you can exploit patterns, the better. Let's take the first sequence here. What's the pattern? I'm adding 1 each time, right? And it goes on forever. And we all know this pattern. Okay, so we can predict what the next 3 terms are going to be, right? 6, 7, 8, and so on. We already know this. We do this all the time. What's the pattern for the next one? I'm multiplying it times 2 each time to get the next one. This is 2 to the 0 power, 2 to the 1st, 2nd, 3rd, 4th, and 5th, and so on. These are also called binary numbers. Okay? Binary meaning, right? So these are binary numbers. This is why, and by the way, computers only understand binary. Even digital, at its core, ends up being binary at some point. Binary is 1s and 0s only. This is why when you go to buy a memory chip of any kind, it's usually of these increments. Okay? Also, like the bit for operating system. So, for example, this new computer here has a 64-bit operating system. You remember Nintendo 64? That was the first 64-bit operating system, and that was like a big deal. Okay, so these numbers are used all over the place. If you take 1 kilobyte, how many bytes is that? It's 1,024. It's not 1,000 like most of the other kilos that we run into. It's close. So if you look, if I look at the hard drive and I want to know how much memory or storage I have left, it'll say that there are so many gigabytes left, and then in parentheses it'll say how many bytes are left, and it's totally different because it's 1,024 bytes to make up 1 kilobyte, and it's 1,024 kilobytes to make up 1 megabyte, and it's 1,024 megabytes to make up 1 gigabyte. So by the time you do all the translations, it's definitely not just moved to 0, right? We've got to do this here. This last sequence here is a little different. It's called the Fibonacci sequence. Some of you might have heard of it before. It's a very, very famous sequence. It says you take 2 units, whatever the unit is, add them together, and then you just keep adding them together to form a sequence. These are 3 different types of sequences. There are lots of different types of sequences. Those who had me before, I did a whole thing on the golden ratio on this. If there's time, maybe later I'll play with that a little bit. But there are patterns all over the place. By the way, at Cal State Long Beach, there's a class there called Discrete Math, where they talk about sequences and things like that quite a bit, and that's called Math 233. It's a Fibonacci number, so no trivia there. Okay, now, we have three different types of sequences. This one I'm adding, this one I'm multiplying, this one I'm adding a couple of elements within it to get the next piece. I'd like to go through some notation. This is a way to write a sequence. Perhaps this is an infinite sequence, meaning there's no bound. All of these are infinite sequences. There's no boundary. Another way that we could write a sequence may look like this. Let's do B. Or B is an integer. No, I should say B is a counting number. It's possible. It's possible n starts at 0. Very rarely have I seen n start at a negative number. On rare occasion at a couple of graduate level classes, we had to sort of work backwards a little bit, but you get the idea. This says the same thing here, but in this case it's going to be there's a finite amount. There are B amounts of these. There are B terms or elements, depending on what we're doing. Now the real power eventually is going to be adding up the terms of a sequence. That's eventually what we're going to be doing. In fact, today's the only day we're not going to be talking about adding up the terms of a sequence. In fact, adding up an infinite number of terms of a sequence. Any questions? All right. Let's take this sequence here. Would you please write out all of the terms of this particular sequence? What is n starting as? 0, then goes to 1, then 2, then 3. How many elements are there total? No? 4, because we're starting with 0, right? 0, 1, 2, 3. Right about, you'll see. What's 2 to the 0 power? 1. Not 0. Yeah, whenever there's a 0 in there, you always want to make it 0, right? But like cosine of 0 is 1, 2. It's like all these weird exceptions. Log of 0 doesn't exist. So what are the 4 elements in this case? 1, 1, 4/3, 2. Now, if you were only given this pattern here, it's very doubtful you'd be able to work backwards and work it backwards. come up with the actual sequence. Yes?
Well, okay, sorry, going back just a little bit, the B terms or elements in blue right there, that's only if n equals 1.
It's starting n equals 1, that's right.
Right, it's right here with n equals 0 we have.
It'd be b plus 1 elements, that's right. We okay? I'd like to give you a couple different types of sequences. Here's what's called an infinite sequence. -1 to the n power over n factorial. Please do not say n exclamation point. You sound so ignorant if you say that. So just call it factorial. I'll define it for you. We'll talk all about it, but just don't say it. That's like my algebra students, instead of x to the 4th power, they say x4. It's like, come on, guys. So let's write out some of these values here. When n equals 0, I'm here. So we don't get nervous, 0 factorial is defined as 1. This is how factorial works. Let's find where this is in our calculator, if we ever need to do factorial. So you're going to double check my 5 factorial since I'm a little iffy on it. So you're going to go to a command line. You're going to hit 5. After you hit 5, you're going to hit math. At the very top, you're given 4 options, and one of them is PRB, probability. I believe it's your first option. Hit enter and see what you get.
20.
Yes. Okay, so there's your factorial button. In fact, real quick, do you want to calculate the odds of winning lotto? Yeah. Let's do it. So it's going to be the one where there's 52 ping pong balls and you get 6 of them. Right? Is that how it works? Yeah. I don't do lottery because I understand math. So what is it? Is it combination or combination? It's combination. So we're going to do this. There's 52 ping pong balls. And when you hit the PRB, when you go to PRB, this is one of those options. So you go 52, you hit that button, then you hit the 6. Is it NCR or is it something else?
NCR.
Okay. Sometimes it's NCK, depends on the calculator.
20,358,520.
20 million plus, right? All right. So one chance and 20 million. By the way, there have been people that have bought all 20 million of them because the jackpot was high enough. They did it in Florida a couple times. They bought every possibility. Yeah, they bought every possibility.
Jeez.
It's a documentary, you can Netflix it, that's fine. Okay, so let's talk a little bit more about n factorial, because n factorial is going to pop up. Let's talk about when we would even use a factorial. Let's say I wanted to take the letters of my name. And what I wanted to do was I wanted to see how many different ways can I rearrange those. So if I have 5 slots, 1, 2, 3, 4, 5, how many possibilities do I have for that first slot? How many letters do I get to choose from? 5. I get to choose from 5. Now that I've chosen one, how many letters do I have? Am I able to choose from now? 4 times 3. So there's 120 different ways to rearrange the name Kevin. Okay, so there's one quick example. Now it gets a little bit more complicated. What about my brother's name? Where we have a double letter in there. Then when you take the one T and you switch with the other T, it's still the same name, right? So you got to divide that out. So there's a whole system set up with this. I want to go back and I want to notice that 5 factorial is the same thing as 5 times 4 factorial. Do you see 4 factorials there? I can also say this statement. Do you see how they're embedded in there? So when we talk about n factorial, this would be the actual definition of n factorial. So in this case, n plus 2 factorial whatever this is, you take one away from it each time. So you start with n, the next one you take one away from n, the next one you take one more away, the next one you take one more away, the next one you take one more away, all the way down. So if I say, what is n factorial divided by n plus 2 factorial, you see that n plus 2 factorial has n factorial embedded in it. You get the idea? Ask questions. You see this by definition is n factorial? So if I do this, what happens? Yeah, the n factorials cancel. How are we doing? When would we run into factorial maybe in calculus? please find the sixth derivative of this.
Yeah.
I know stuff. Not a lot, but I know some stuff. So we end up with a factorial in here. In fact, this is actually going to help us build a famous formula called the Taylor series. We okay with the factorial? We'll review it again.